Hey, what's up? Here we go. Last video in the series of specific heat. Using our specific heat formula, we have Q, which is energy or heat, equals mass times specific heat times change of temperature. Remember that little triangle right there means change, all right? We have had a video on solving for Q. We have had a video on solving for M and C. Now, the final of this series, we're going to solve for change of temperature. This is going to go down basically exactly the same way we'd solve for mass and specific heat. There might be another element or two to it. So that's what we're going to kind of talk about first. First thing, what we're going to do is we're going to rearrange this equation so that we can solve for the change of temperature. So we have four spots in this formula. 1, 2, 3, 4. We have Q, M, C, change of temperature. So just like when we was trying to solve for mass in the last video, or trying to solve for specific heat in the last video, we have to rearrange this formula so that our missing variable is on a side by itself. So here's our equal sign. We have this side of the equation. We got that side of the equation. Now, we need to find the change of temperature. So, to find the change of temperature, this needs to be isolated, similar to how Q is isolated here. To do that, we need to get rid of this stuff, right? That's our goal. It may not work out that way, but that's what we're going to try to do. Our rules are very simple, two things. I'm going to do the opposite of what is already there, the inverse action of what is already there. That's going to allow me to move it to the other side. That's the first rule. Second rule is whatever I do to one side, I'm going to do it to the other side because that's what you got to do. I don't know who made the rule, but that's the way it goes. I can multiply this side by 275,000. That's fine. I don't know why I do it, but as long as I do it to this side over here too, then we're good to go. So to move these, right, I'm going to kind of knock this out in one step since the last video we did moving in one at a time. So here I see multiplication. M times C times change of temperature. So there's multiplication all across the board, right? So I can move this MC together, right? Since it's multiplying, it's not different action. So I'm going to divide this side by M times C. That's what we got here, M times C. Whatever I do to this side, I'm also going to do over here. So I divided this side by M times C. I'm going to divide this side by M times C. All right, I'm going to take a look at this. Now I got M and M top and bottom, C and C top and bottom. Right, they cancel out. And when I say they cancel out, they gone. Right, they are now one. They now no longer affect the outcome. So now we have change of temperature by itself, QMC, all up here together. So we have rearranged this formula. Change of temperature equals Q divided by mass times Celsius. Getting to this point, all we're going to do, we're just going to plug in our numbers and we'll be good to go. I'm going to show you a couple different scenarios of how this could kind of come down. First is just straight up find the change in temperature, right? I'm going to use the same numbers we've been using this whole series. If I have 8,000 joules, if I have a specific heat of 4 joules, gram degrees Celsius, and if I have a mass of 200 grams, right, what is the change of temperature? I just throw them in as a formula right here, and it will be good. So, change of temperature, Q is joules, right, 8,000 joules, right, M is grams, so 2,000 or 200 grams, C, specific heat, 4. Remember, this gram degrees Celsius technically gets slipped up on the top. We kind of just don't do that at this level until later on in the year. We're ready to start doing that. But you can go ahead and start doing that now. That'd be awesome. So we just solved this for our change of temperature here. We got joules, joules, grams, grams. Our answer is in degrees Celsius. That's exactly what we want, right? Degrees Celsius. Sorry about that glare out there. Anyway, change that. Ain't gonna have to. Guess all of them kind of got that glare on it, don't it? Anyway, so we got 200 times 4 on the bottom, 8,000 on the top here. So what I'm gonna do is kind of go ahead and finish it out. 0, 0, 0, 0. So we got 80. In there, 80 divided by 2 times 4 is 8. 80 divided by 8 is 10. All right, so we just simply found our change in temperature here. That's the simplest of what could happen. Just bear with me a little bit. I'm gonna move these kind of over here. Thing got me all jacked up now. So same numbers, 8,000 joules, 200 grams, 4 joules grams per Celsius. All right, so now kind of something we can add to this, add a wrinkle to this. Let's say if the original temperature was 22 degrees Celsius, and I just made that number up off the top of my head, but we can say if this is the original temperature, then what is the final temperature going to be? So we're going to use our same formula we did a while ago. All right, just always don't try to memorize the formulas. Just start with your base formula, move them real quick. It takes like 2 seconds once you're good at it. All right, I got multiplication here. I'm going to divide by MC, divide by MC. All right, my formula is Q divided by M times C equals change temperature. It takes like 5 seconds. Just start from the original formula. It eliminates the mistakes. You'll be right all the time. So I'm going to plug these numbers in again, right? Just like we did last time. So 8,000 joules divided by 200 grams times 4 joules, grams, Celsius, grams, Celsius. Oh, Celsius don't cancel. Joules, 0, 0, 0, 0. So I've canceled all this out. Now I have 80 divided by 2 times 4 degrees Celsius is my answer. So 80 divided by 8 degrees Celsius is 10 degrees Celsius. So my change in temperature is 10 degrees Celsius. I just reworked the same problem we did last time. All right, we're giving basically the same information: 8,000 joules, 200 grams, 4 joules per gram degree Celsius. The only thing new this time is that it says the original temperature was 22 degrees Celsius. What is the new temperature? What is the final temperature? So we have found the change in temperature right there, right? This is the original temperature. There's no evidence to say that the temperature was removed. If the temperature or if the heat was removed, that would have been a negative sign right there. That would tell us, hey, this heat wasn't added to it. It was released or it was removed from the system. So that in case, which means that it was added. A lot of times it will say 8,000 joules was added or some kind of form like that. So we're going to take this 10, we're going to take this 22, we're going to add them together. When you're adding, do not cancel units. Doesn't work that way. Only in addition, or only in multiplication and division, sorry. So we're going to get 32 degrees Celsius is our final temperature. Now, what if this had been a negative? What if the temperature was released or was removed from the system? What would happen then? Let's set it up. All right, same formula, right? Change the temperature equals Q. So now our Q is negative 8,000 joules. Negative 8,000 joules. All right, our mass is still 200 grams. Our specific heat is still 4 joules per gram degree Celsius, and we're still starting at 22 degrees Celsius. All right, I look to see if anything cancels. Joules, joules, grams, grams, 0, 0, 0, 0. Right, again, we're left with 80 over 8 degrees Celsius, but now it's negative, right? It's negative, it can cancel out. Before it was just 80, now this negative, don't forget about it, it stays there. This is going to give us negative 10 degrees Celsius. So our change in temperature is negative 10 degrees Celsius. So if we started originally at 22 degrees Celsius, the temperature change is negative 10 degrees Celsius. Then the new temperature, the final temperature, whatever it says about the ending temperature is, it is 22 plus negative 10 or minus 10 is going to be 12 degrees Celsius. So that's it for this video. You have seen we have rearranged this formula to solve for delta T. We did that in the exact same way we do all of our equations or our formulas. We're going to do the inverse, which is the opposite of what is already there, opposite action. Opposite of multiplication is division. Opposite of division is multiplication. Opposite of addition is subtraction, so forth, so on. We do that. whatever we do to one side, we do to the other. This is going to cancel things out. It's going to move a variable from one side to the other. We keep doing that until we get the variable isolated that we want. No matter how many times we got to do it, it'll get you there. So we did that. We solved for change in temperature. Then we worked the problem by just solving to find the change in temperature, which was 10 degrees Celsius. That was the first thing we did. Then we added in this wrinkle here, 22 degrees Celsius. We said, this is our starting temperature right here. Now, if we add the energy or if we subtract the energy, this one we're going to do two different things at the end. If we're adding the energy, if we don't have that negative, right? If our joules is positive, then at the end we're going to we're going to have a positive change of temperature. We're going to combine it with our original temperature to give us our final temperature. If we were removing this heat, if it was being released, we would have had negative, which would have gave us a negative change of temperature. So when we combine that with our original, our temperature got smaller. So this is the end of the specific heat formula series. If you'd like me to clarify or do any more examples of anything, whether it be finding Q, mcT, if you want to give me a specific example of a problem, just leave it in the comments. I'll look at them one day, I guess, and see what I can do. All right. Till next time.